Hello my people, hope we're doing well. This is video 2 on our unit on using Trig IDs. And this is largely, like I said, using them to change the form of an expression into one that is simpler or simply more usable. The first one up here, let's go ahead and get started. Use the fundamental identities to change the expression to one involving only sines and cosines, then simplified to a basic trigonometric function. Yeah, I have no idea. My printer doesn't like it when I take stuff and print it to PDF from a Word document. Sometimes it sort of moves the letters around. It really kind of is annoying. It's fine when I look at the PDF, but when I print it out, it just goes wonky. So we have tangent over cosecant squared plus tangent over secant squared. Now it says that I need to change the expression into one involving only sines and cosines. And so this first expression is going to be sine over cosine. And then I'm going to multiply it by the reciprocal of the denominator, which is times sine squared x. Then I'm going to take this right here, and I'm going to call it sine x over cosine x. And I'm going to multiply this one by the reciprocal of the denominator, right? Because when you're dividing by a fraction, and both cosecant and secant are implied fractions, it's the same as multiplying by its reciprocal. Well, how many terms do I have here? It's kind of deceptive because it's notationally large, but I really only have two terms, term 1 and term 2. Let's go ahead and factor out what is common to them. We can factor out a GCF, and when I factor it out of the first term, I'm left with sine squared. When I factor it out of the second term, I'm left with cosine squared. Oh my gosh, will you look at that? That's equal to 1. Well, then simplify to a basic trigonometric function. If this goes to 1 and sine and cosine are tangent, then basically that whole thing was just tangent, which is funky. Okay, let's go ahead and look at the next one. It says cosine squared minus 4 over cosine x minus 2. And the thing is that what we need to, it's difficult when you're just starting out to look at something like cosine and see it as one quantity, because it's, you know, C-O-S and then an X. It's four different strokes of the pen. Actually 5 if X winds up being 2 strokes of the pen. It's 5 strokes of the pen, 4 characters, but it represents a single value. And so this means this. Well, I don't care what's in those parentheses. That's something squared minus something else squared. That's the difference of 2 squares. And that means that I can factor this into a plus b and a minus b. And if that's the case, boom, boom, I get cosine x plus 2. Okay. That, and I'm going to keep saying this, that is far preferable to deal with than that. It has several advantages. First of all, it's not rational. Second of all, there's nothing squared. Everything's of the first and the 0 degree. So being able to take these trigonometric identities and using them to change the form of things is going to be extremely, extremely useful. Okay. Now, here we're going to be combining the fractions and then simplifying, right? Because oftentimes in the midst of a problem, you need to basically push something into a single expression, and then after it's in a single expression, you need to be able to simplify it as much as possible so that it can then be usable. Okay. Now here we have 2 fractions with different denominators. We of course need to find a common denominator. And let's say I had 1/2 minus 1/3, right? If I had 1/2 minus 1/3, you would get a common denominator. Since they're relatively prime, you would multiply this one by 2 over 2, and you multiply this one by 3 over 3, right? Well, this is same thing is going to happen here. This one, you need to multiply by secant x plus 1 over secant x plus 1. Over here, this is going to be secant x minus 1 over secant x minus 1. The great thing about this, however, is you're going to get secant x minus 1 over secant squared x minus 1. And you're going to get the same denominator over here. Well, that's kind of neat, because remember when we were dealing with our fundamental IDs, one of the forms of this Pythagorean identity is this, when you basically just subtract 1 from both sides. So secant squared minus 1 is equal to tangent squared. Okay, well, let's not do that just yet. Let's go ahead, since they have the same denominator, let's push them together. Now remember that numerators and denominators are functionally, they serve the same, one of the purposes they serve is the same as parentheses, right? So if you have a negative out here in front, that needs to be distributed across the whole thing. And that's one thing that in our haste sometimes we forget. And so this is going to be secant x minus 1 minus secant x minus 1. And let's go ahead and change that denominator now. That's tangent squared x. That's going to be negative 2 over tangent squared x, or negative 2 cotangent squared x. That is much simpler than that. Okay? And now I hope by walking through this, you're starting to get an inkling of why this is valuable. This is valuable for the same reason that the properties of logarithms or rules of exponents is helpful. Sometimes changing the form by using these means completely revamps the entire problem and turns it into something far preferable. Let's go and look at this one down here. Let's go ahead and use the same strategy. There is another way to do this one, but let's go ahead and use the same strategy as we did on the one above. Let's go ahead and multiply this one right here by this denominator over itself, 1 minus cosine x over 1 minus cosine x. And we'll multiply this one by sine x over sine x, right? And what we'll get here is sine squared x over sine x, 1 minus cosine x. I'm going to leave it in factored form in the denominator. I have this suspicion that something's going to cancel. 1 minus cosine x squared over sine x, 1 minus cosine x. Now, don't you dare distribute that exponent, okay? That's one of those pet peeves. But we do need to go ahead and push them together. And when I square 1 minus cosine x, remember, because it's squaring, it's the same as squaring cosine x minus 1. And that becomes cosine squared x minus 2 cosine x plus 1. All of that over sine x, 1 minus cosine x. Now, this right here ought to look really, really familiar. And if I go ahead and join it with that 2 right there, I get 2 minus 2 cosine x over sine x, 1 minus cosine x. Oh my gosh, will you look at that numerator? They both have a 2 in there. Isn't that just neat? Boom, boom. And this winds up becoming 2 cosecant x. Now there is another way to do this, okay? I will go ahead and show that to you real quick. Let's go ahead and copy that down. We have sine x over 1 minus cosine x. Now, just like when you're playing chess, and I don't know how many of you are chess players, your actions in this move will have everything to do with what you want it to look like, what you want the board to look like, 5, 10, 15 moves down the road in the game. depending on how good you are. I unfortunately never had a great regular teacher at chess when I was a kid. Chess is one of those things where they just don't have chess clubs anymore. I digress. Now, in the original one that we just did, we basically multiplied each one by the denominator of the other over itself, which is a perfectly legitimate way to do this. But remember that I need to not only know these, I need to be able to employ these strategically. If 1 minus cosine squared is the same thing as sine squared, I can actually multiply this one by sine x over sine x, and I can multiply this one by 1 plus cosine x over 1 plus cosine x. And the reason that I can do that is because these denominators are conjugates of each other. Now, conjugates, remember, is that really fancy way of saying when I multiply them together, they will create the difference of two squares, right? And I'm going to go ahead and do that. Now, I did it this way. Those have different denominators, but now they don't. Okay, and I strategically did that so that they would now have the same denominator. And let's go ahead and distribute as we combine those fractions. So, and all of that is over sine squared x. Well, that and that cancel out, and I'm left with 2 sine x over sine squared x, or 2 over sine x, or 2 cosecant x. And it's the same exact answer. And I arrived at it in a completely different way. Okay? There's another way to do it, but I would be getting ahead of myself, and it would be sort of intruding on what we're going to be doing in the next section. But we're going to need to remember this style of question. Let's go ahead and it says factor the expression and use the fundamental IDs to simplify. And sometimes, of course, it's not going to be in that order. Sometimes we're going to need to use the fundamental IDs to simplify and then factor, like in this first one. You can't factor this because they're not consistent, right? But if I do change this, and they've sort of given us a heads up by putting that, by putting those last two terms in parentheses, that becomes that. Which, you know, I don't like it in that order, and thankfully I know how to flip it around. That is what I usually refer to as quasi quadratic, and usually textbooks say an expression in quadratic form. Yeah, I mean, because it's not quadratic, because it's not a polynomial. It has trig functions in there, right? But it's of this form. It's of a quadratic form, and therefore it can factor in this. Oh, sorry. Yeah, I almost did a no-no. It can factor in the same way that a quadratic can. And therefore I get sine x minus 1 quantity squared. Okay? And that is much simpler than that. Now, it isn't as simple as maybe some of us would like it, but it is simpler. Now let's go ahead and move down to this one. We see secant squared x minus secant x plus tangent squared. Well, that's a little more difficult. Here's the thing. I want them to either be in terms of secant or in terms of tangent. I can't get them all in terms of tangent because while I can change secant squared into tangent squared plus 1, I have no way of changing the secant. So what I'm going to have to do is I'm going to have to change the tangent squared, and I'm going to get secant squared x minus secant x plus secant squared x minus 1. And when I need to reorder this, in order to factor, I'm going to get that. Now, that, of course, is of the form 2u squared minus u minus 1. Now, Does that factor? Indeed it does. You get 2u and 1 and u and 1, and you need this middle to be a -1, so the one that gets multiplied by the 2 is negative, and the one that gets multiplied by the positive, by this other u, is positive, and therefore this becomes 2 secant x, plus 1, and secant x minus 1. And that is the factorization that we're looking for. Now, a lot of this is sort of foreshadowing things to come. Like, if you had such and such, blah, 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 equal to 0, right, and you were asked to solve that equation, you would need to get it into a form that is factorable equal to 0 in order to do that solving of the equation. Now, a little bit more frustrating is this one. And you're thinking to yourself, is that sine cubed plus cosine cubed? And the answer is yes. All right. Now, do we happen to remember our sum and difference of 2 cubed factorizations? I hope so. That's another one of those things that's just assumed when you go into calculus that your factorization skills are up to snuff. And if I have to, bludgeon them into you, I'm more than willing to do that. I will make that sacrifice for you guys. Okay, and there you go. Well, that's kind of neat. Okay, let's go ahead and use this form, and u, of course, is my sine, and v is my cosine, and I'm going to get sine x plus cosine x, and sine squared x minus sine x cosine x plus cosine squared x. Well, a little bit short on. But here's the thing. This and this added together are 1. So actually, this further simplifies to 1 minus sine x cosine x, and that is my full factorization. So if this were embedded within something where I needed to solve, this factorization would help us. And actually what you'll learn is that when we get to section 4 of this unit, you can actually simplify that sine x times cosine x with an additional identity that you'll learn a little bit later. The last thing that we need to talk about, and this is another one of those things that's offered purely for the sake of foreshadowing. You might think to yourself, what good is this? This just seems rather arbitrary. Well, a lot of the things that you think of as arbitrary, textbook writers sort of embed within the lessons and the exercises in order to foreshadow things that are coming. This is not a topic that we will get to this is not a topic that we'll get to this coming year, since it's part of the BC curriculum. But there is a form, there is something that requires trig substitution when you're doing integration, which is one of the calculus operations. But what we need to do is we need to basically take this and plug it in for x, okay? And so we get 2 secant theta squared minus 4, or 4 secant squared theta minus 4, or 4 times secant squared theta minus 1, and oh my gosh, secant squared theta is tangent squared theta. So all of a sudden, I have taken something that was not capable of being simplified, largely because it was 2 terms and was not a perfect square. And by means of a clever and strategic way of substituting, the great thing about those Pythagorean identities, and this will come up again and again and again, the great thing about those Pythagorean identities is they are one of the few ways that you can take something that is 2 terms and change it into something that is a single term. And that's really, really nice when you're underneath a radicand or when you're in the denominator. Like monomial denominators are great for simplification. Binomial denominators, not so much. And based upon what we're doing right now, we won't deal with I mean, this is an expression, so we're being given the positive, but we won't deal with all the absolute value and stuff like that. But what we have is that, okay? And of course, what you would need to do is when you use this sort of trig substitution, obviously at some point you will need to sort of change it back into your original variable, but we won't deal with that right now. As I said before, this is just a matter of foreshadowing. And so what we need to do is the same thing in this particular problem. This becomes root 10 sine theta, the whole thing squared, and that gives us 10 minus 10 sine squared theta. Well, that's kind of nice, because then when I factor out that 10, I get 1 minus sine squared theta, or root 10 cosine squared theta when I use the Pythagorean identity. And now I'm going to get root 10 cosine theta. Okay, and that's good enough for right now. Like I said, this is just for the purposes of foreshadowing. But you know, even simple exercises like this that don't have immediate payoff give us an excuse to play with these identities and see the various ways in which they can be used for the sake of changing the form of something. And just simply the repetition in terms of utilizing them in the midst of this variety of different types of problems embeds those identities deeper into our long-term memory and basically allows us to memorize them just by virtue of using them rather than having to pound it out by flashcards or some other artificial means. I hope that this has been a good supplement to our discussion in class about using trigonometric IDs. I think that even if you get to the end of this day of 5.1 and are still a little bit confused, I think that things will solidify in the several days that we spend on 5.2. Because 5.1, 5.2, 5.3, they're all related, and they all have to do with changing the form just for different reasons and with different outcomes. Okay. If you have any further questions, please do shoot me a chat message or an email. Bye.